Yeah, I don't think it'll work.
I think you need to create like group.
Yeah,
And then after the part that
that's what she said. Yeah.
Okay, everybody, let's get started for today. And now my video is live. Let's see here. Welcome to the second day. There's our calendar there that you can see. I have the first 3 video modules up. I finished the third one this last weekend, you can see. We're there at week number 2, the live in-person part. And so again, I try to divide the weeks up into lecture, which we are at right now, and video module. The video module for this week's about 90 minutes, so I'm going to try to stick today to about 60 minutes for the week. I pretty much try the best I can to be respectful of your time and not going to go over 150 minutes many weeks. Most weeks we'll go a little bit under, and I do keep track of it, so if I ever do go over, you'll get the time back. All right, so let's see. Before we get started today, I've got a couple of questions that I either have on Canvas or email that I'm going to talk a little bit about. So let's do that, and then I'll open it up for general questions. First thing I want to talk about a little bit is discussion forum versus email. So you can email me questions. You can also put them on the discussion forum. If you put them on the discussion forums, it's a little bit easier for the other people to see it and so on. And so it's archival also. So I've tried to set up a number of discussion forums here. So, if you have questions about a video module, if you'll put it in the video module discussion and general Simio and so on. I tried to make this as user-friendly as possible. And so if you would do that, unless you have some compelling reason to email me, if you would rather, if there's a particular reason you don't want to share with the rest of the class, that's fine. You can email me. The one thing I would ask is if you do email me, copy Grant, who I forgot to introduce, our TA, Grant Romine in the back there. The reason I want you to CC Grant is because Grant is in charge of keeping up with class participation. And so when you email me, that's class participation, and Grant needs to know it. Yes?
So I have found it to be extremely hard to get pictures into Simio, or not Simio, gosh, into Canvas.
Okay.
Do you have any suggestions for that?
you need to upload it. Like in your user profile, you need to upload the image and then you can
Okay.
It's not friendly way.
Yeah, that sounds pretty painful. So maybe that's a use case where it's easier to email me. And again, this is not a hard and fast rule. If it's too painful to do pictures, you can always email me because I can then put those in the discussion forum also. Okay, so I got a couple of questions here today. First one was a suggestion that I spend just a couple of minutes talking about arrival tables. I talked a little bit about them, and we did them in the Simio refresher, but my understanding is that we don't cover arrival tables in the undergraduate class. So I just wanted to spend just a second talking about those. Pretty straightforward concept. In the model that we did in the Simio refresher, we had the tandem queuing system, and the last model that we did was the arrival table model. And so you can see we have a source object here. And so the kind of the standard way that people think about a source object is that it generates arrivals according to a random inter-arrival process or using random inter-arrival times. Simio has several different arrival modes that you can use. If you look over here, this arrival mode, this default one, inter-arrival time, if you have a non-stationary Poisson arrival process, you can use that time-varying arrival rate. You can also use an on-event, so when an event occurs, it generates an arrival. We'll see some of that at some point during the semester. I'm not exactly sure when. And then we have this arrival table. The arrival table concept basically says, I have a data table here, and my data table includes at least one column that can be interpreted as a time. And so you can interpret either numbers as time or a date time. Okay, so either one of those are going to be interpreted by Simio as a time. And so what happens is when you start the simulation, when it gets to that particular time, it generates an arrival. The important part also here is that in addition to generating the arrival, it sets a row reference to that particular row. So for example, when the simulation time gets to, say, 1:33, this would be in hours, I'm going to generate an entity at that source, and that entity will have a row reference to row 9 in the table. And so it's that row reference that lets us have access to those different columns like you see right here. So I have the arrival table dot p time 1. And nowhere here do I say, hey, go to row 9, right? I don't have to say row 9 because that row reference is set. And that's an extremely powerful feature that we use over and over and over. And as we see in this week's video module, if you have relational tables, the relationships hold, okay? So we use that feature a lot. Yeah?
In the video module, like, I can see that the arrival time is ordered in an ascending order, but the table that we have in the case study anyways is not in order the arrival time. But like I copy the table, run the button, and it's working. So I'm assuming like I don't need to order them.
You do not have to have the table. The table does not have to be in order. So if I were to go in here and put a row at the end and say, okay, arrive at time 0, it'll arrive at time 0. Okay? So arrival tables we will see a lot in scheduling type models. We usually don't deal with random arrivals. You deal with scheduled arrivals. And sometimes we have some randomness around those scheduled arrivals, but by far we use scheduled arrivals more than we do random arrivals. So interactive logging, I got a couple of questions on how to make sure that we have interactive logging. There are 2 steps you have to do highlighted here. The first one is in the Run Advanced Options menu. You have to enable interactive logging. And then for all of your object instances that are based on the server, which would be the server, the combiner, the separator, and any objects, custom object that you've developed based on those, you have to set log resource usage to true. One thing that I learned today, thanks to a couple of your colleague students, is that if you have the student edition, this is probably not enabled. So if you pull up a object instance and you can't make this true, that's probably an indicator that you don't have the license set correctly. Okay, so check the license using the support ribbon, and if you still have that issue, contact me. And when you contact me, if you will just send me what I need to see is from the support ribbon, I need to see this section right here, because it's got the version of Simio that you're using plus your license type. And if that says student, then you probably don't. You're not going to be able to use that particular license for this class. But as I said, we have a class license for Simio, RPS Unlimited. And so it's easy. You just have to follow the instructions to use that license. Okay. Let's see here. Okay. Next question has to do with this notion of model entity versus default entity. In particular, if you look at the model that we did, the dispatching model that I did in the video, so the dispatching model right here, what I did was I wanted to use dispatching rules at the S1 and S2, so I assigned the processing times at the source. So instead of sampling at the server instance, I sampled all of the values when the entity arrived at the source. Okay, and so to do that, in the model entity, I had to have 2 states, P time 1 and P time 2. So I have these 2 states associated with model entity, and then I assigned those state values in the source object. Okay, so go back and see what do we do? Back to my dispatching right here. Just assign those 2 values. So just sample an exponential distribution exactly like we did in the baseline model, except I did them all at when the entity arrived. And what that let me do is the entities that are queued up in front of S1 will all have all the processing times set. So I will already know what those processing times are, even though I sampled them randomly. And that's what lets me use different dispatching rules like SPT or something to do the selection. We also had this plot, the status plot, and what we're plotting here are the number of entities in system. So we're plotting the instantaneous number, which you get with default entity.population.number in system, and the average over time, which is default entity.population.number in system.average. Okay, so we talked about this. And so this root of this question that I got was, I can't pull these both up, but when we did our source assignment, we assigned to model entity.ptime. When we did the plot, we used default entity.population. So sometimes we use default entity, sometimes we use model entity, okay? And this comes from this notion of the object hierarchy within Simio. We have an object definition, which defines the structure of the object, and it lives in the library, either the project library or the standard library or some other library. We have the object instance, which is created when you drag something from a library into the facility view. So you're creating an instance of that object definition. And then we have the run space, or sometimes called the realization, which when you click go, it creates those. Okay, so if I look at my model running, I look at this model. Model entity here is the object definition. Default entity here is the instance. And when I run the model, each one of these guys is a realization. Okay? So this notion of when do you use the definition and when do you use the instance is a little bit nuanced and a little bit confusing. Okay? The best rule of thumb that I tell people is as follows. Anytime you need any kind of population information, you use the instance name. So if I use default entity, or if I rename that part 1 or part 2 or whatever, anytime I need information about the population of run spaces, you use the instance name. Any other time you use model entity. Therefore, the easiest thing to do is that when in doubt, try model entity, try it, and if it doesn't work, try the instance name entity. Okay? Usually when I'm dealing with the structure, like assigning state values or inquiring property values or something like that, I need the definition, which would be model entity. Where anytime I'm dealing with a specific realization, okay, a specific realization, then I'm going to use default entity, the instance name. Okay, so no crisp answer there, just a rule of thumb that if you're dealing with the population, you typically use the instance name, and otherwise try default entity and just sort of see if that works. Okay. How to compute utilization. Okay, so I thought I'd spend a little while talking about this one because this is an important question, something that comes up all the time. So let's think about this notion of what utilization is. Okay, so I'm going to draw on the board here and say, let's just think about that I have this arbitrary system. Okay, here's my arbitrary system. And I have things that arrive and are processed and things that leave. Okay, and I run this for some period of time. I have a simulation of this. And I say, well, what is the utilization? You know, what do we think about when we use the term utilization? What we generally mean is something like the used, that we have some notion of the used capacity over the overall capacity. Okay, so it's something like the proportion of used capacity. Okay, that's the kind of the general concept. And if you have a simple system, like if you think about a server in Simio, just a default server, you can compute that by just saying, okay, this is something like the busy time divided by the total time. Right, so I do the busy time divided by the total time. That's this notion of what utilization is. Right? So let's just think about the case where I have an object, a server object that takes 12 minutes. So the service time here, the mean service time is equal to 12 minutes. Okay, so what does that tell me? Well, it tells me that my rate that I can serve, that I can process entities, if we do this in per hour, this is going to be 60 divided by 12, 5 per hour. Okay, so that's my capacity. Now suppose that I run my model for 10 hours, and I create or process 40 entities. Right, I process 40 entities. Then if I look at this proportion of used capacity, my capacity, which we generally reference as, my utilization, which we generally reference as rho, is going to be 40 divided by 5 times 10, 0.8. Okay, really straightforward. And Simio calculates this for you and tracks it. So if you do server 1 dot capacity dot scheduled utilization in a simple model, this is what you'll get. Okay? Now, things can get a little complicated when you do things like work schedules. So for example, suppose that I did a work schedule where I said, I'm going to work, the standard work schedule where I'm going to work from 8 a.m. to 12 noon, and then I'm going to take a lunch break from 12 noon to 1 p.m., and then I'm going to work from 1 p.m. to 5 p.m., right? So the first rows are AMs, the last rows are PMs. So this is a 4-hour period. This is a 1-hour period. This is a 4-hour period, so they're total 9 hours. Now suppose that the server was busy the entire time that it was working. So during the 4-hour block and the 4-hour block, totally busy. The question then is, well, what's the utilization? Is the utilization 8/8 or is it 8/9? Right, because I have 9 total hours. It's only busy 8 of those hours. 8/9 seems reasonable. On the other hand, I have 9 total hours, but it was only available 8 of those hours. So 1 seems reasonable. So the answer here is, well, there is no answer. It's not right or wrong. It's the interpretation. It's how do you interpret utilization. So in this case, it's a little bit trickier, but still pretty straightforward. Okay? Now think about if we have a slightly more complex system like the one that you have in case study 1, right? Where I have, okay, here's my box, and let's say that I have parallel servers. Okay, and these guys come, and let's just say for the sake of argument that my service times here are different. So this one is 12, let's say this one is 10, and this one is 15. So those are the respective service times. And then I say, well, for this box, this station, what's its utilization? Okay, and in order to compute its utilization, we have to know its capacity. Okay, so I can do that because we know in the parallel system, the capacity or the capacities are additive. Okay, so this one is going to have a capacity of 60/12, which we just computed up there, which is 5. This one's going to have a capacity of 60/10, which is 6. This one's going to have a capacity of 60/15, which is 4. So my overall capacity is 15 per hour. So using that overall capacity, if I said, okay, over a 10-hour period, I had 100. My utilization is then 100 divided by 150, 2/3. Okay? Now when you run the model, depending on how you made this decision when entity gets here, whether they go here or go here or go here, Simio or whatever software you're using is going to compute a utilization of these individual ones also. But the interest here in a station like this or in a system like this is what's the overall capacity. Okay, and then you can look at the other general type of system where suppose I had the same thing, but they were serial. Right, so I have something that looks like this. And same thing, 12, 10, 15. And I say, okay, well now what's the capacity of my system in the box? What is my capacity? Right, so I've already computed these guys. This one is 5, this one is 6, and this one is 4. So my capacity here is 4. It doesn't matter what I do, I'm never going to get more than 4 per unit time, or 4 per hour. Okay, but once again, if I run this, I'm going to get a utilization for this one. I'm going to get a utilization for this one. I'm going to get a utilization for this one. But the utilization for the thing taken as a whole is 4. Okay, so this question of how do I compute the utilization in anything other than the simplest system, it's more than just one number. It's, okay, well, what is it that we're really looking for? Okay?
So for the case study, can we just compute the individual ones? Like just...
Until I got the question on Canvas, I really hadn't given that any thought of what I was looking for, whether I was looking for an overall utilization or whether I was looking for just the standard, whatever you call it, server 1 dot, server 3.1 dot capacity dot scheduled utilization, server 3.2, And so ideally, if you run long enough, they should be equal, right? Because if you think about it, in the case study 1, all of these service times are equal. So if the service times are equal, if you have any kind of equitable distribution, whether it's random or whether you use the overload function, if you run it long enough, those 3 utilizations should be the same. Okay, and again, that's another case where you should experiment with it. Okay, but as I put in the Canvas discussion, if you want to compute this, it's pretty simple, but you have to do it, right? Because Simio doesn't have any way to know, hey, they might be interested in this utilization because Simio sees this as 3 parallel servers. It doesn't see it as this, with this box around it as station 3. So if you want to compute that utilization, you have to do it. Yeah.
Since what we get out from Simio is also the scheduled utilization number, which is a number between 0 and 1. Can we add them up since they are all the same capacity and just divide by 3?
In some cases you can, but in general you cannot. Yeah, so I would not do it that way because only in certain cases is that going to be valid. Like everything has to be equal and the distribution has to be random.
Yeah, I mean, like when I say divide by 3, in a general case, we would do a weighted sum.
Yeah, you could do a weighted sum too. You could, but if you're doing it in simulation, just compute it. Let the simulation track it for you, rather than trying to figure out, because that's the whole idea of doing the simulation, is so that you can track that value. It's always good to try to figure this out because, again, we go through this verification process. How do I know I've implemented my system correctly? Well, so it's good to have some expectation. So, for example, my expectation to the question was, if I run this long enough, all 3 of these utilizations for the case study, since these are all equal, should be the same. So you should run it and look and see and compare what you see to your expectation. Right? That's part of the verification process. It might be that my expectation's wrong and the model's right, but that verification process is converging those 2 things, the expectation and what you actually see. Okay? I think that's the last question I had. Yeah, that's the last question for today that I got in email or on Canvas. So here, stop that. So before I start talking about general scheduling, does anybody else have any questions for me?
What do you expect for the write-up for the case studies? Like 2 pages, 3 pages?
If I want anything in detail, I will specifically ask for it. Like I think for the case study 2, which you guys haven't seen yet because we haven't finalized it, I say something like, give me a screenshot of the resource plan or something. And sometimes I might say, compare these 2 models and discuss. I would just want you to have a general discussion. For this one, not much. Just, okay, here's what I have. Right? So I try to be more explicit if I want you to discuss more. There's no need unless I explicitly ask to talk about the details of the model. If I want you to talk about particular modeling aspects, I'll specifically ask that. Okay? Yeah.
So my first question is there a rule of thumb for the warm-up period?
Is there a rule of thumb for warm-up period? The rule of thumb for warm-up period is it can never be too short. It can never be too long. No, there is really no rule of thumb. Again, the closer you are to your capacity, if I take any one of these systems, right, the utilization is going to be determined by the capacity and the arrival rate. The closer I am to my capacity, the longer my warm-up needs to be. Okay, so in this system, if I'm looking at steady state performance, if I have a really slow arrival rate, it's going to warm up quickly. If I have a long arrival rate, it's going to take a while. But there's really not any general rule of thumb to try to figure out what that should be, other than doing some experimentation.
I have another question.
Okay.
So for server 3, when we use capacity 3 and then we separate them one by one, I got some different results. By my expectation at the beginning was, since I'm using connector, I use connectors, 0 time travel, travel time is 0. I was expecting to get the same results, but when I see different results,
Okay.
I'm a bit confused and I cannot find just so much clear explanation for this one. Maybe we discussed some and maybe.
Well, again, tell me what you're trying to do. So what you're saying is that you would expect if you have a capacity 3 server versus 3 parallel servers where you have random, that the number should be the same? Okay, so what I would expect to happen is the utilizations would be the same. The timing queues would be different. That's my guess. Because what happens is when you have a capacity 3 server, as soon as something is available, you get it. Whereas if you have parallel servers, if you make the decision of which queue to get in, you might make a bad decision. So think about the capacity 3 servers, you're putting off the decision to the last minute possible. Okay? Other questions for me? Okay. Erase this guy.
So for this case, we use also when we use pairs instead of connectors, we will have a bit more different.
Yeah, if you use path, so if I connect things with path, then the transport time, well, the transport time depends on two things if you use a path. Length of the path and the speed of the entity. If you set the entity speed to infinity, it's going to be just like a connector. If you don't, then it's going to be the distance divided by the speed, and so that delay will be there. So for a queuing system, it's just going to be a fixed addition to the time. It's not going to have any impact other than increasing the time. Okay, let's talk about scheduling, dispatching, schedule generations, 424. Don't think we're going to get through with this today, but that's okay. So we talked about scheduling back on the introduction, basically said the idea of scheduling is that we want to allocate resources that have a fixed capacity, and we want to do that over time. And so I have this example where I have 3 resources and I have 7 jobs, and I have 2 different schedules that we see. And so we think about this notion of scheduling. The act of scheduling is basically taking this information and creating something that looks like this. Okay, creating something that looks like that. So we're going to talk about a little bit of detail here today. And let me say, this is my theory, not theory warning here. We have non-OR people here. They're going to say, man, some of this sounds a lot like theory. The OR people are going to say, no, this is not theory. This is just definitions. We haven't gotten to theory yet. So we're not going to do theory in the class, but we're going to do some definitional things that might sound a little bit like theory. But no worries, we're not going to do theory in the class. So when we talk about scheduling, so scheduling is a domain in and of itself. You know, I've taught an entire semester-long classes on scheduling. We have classes here, graduate, undergraduate. People, you know, there is a very healthy literature on scheduling. So scheduling in and of itself is a very complex and well-studied field, okay? Our focus in this class is really just on a very small subset, simulation-based scheduling, okay? But we need to talk a little bit about the kind of general scheduling terminology here. And so when you think about traditional scheduling problems, I have a set of them here. Single machine scheduling, where basically I'm just focusing on jobs that arrive to a machine, and I'm trying to decide how to schedule those jobs on that single machine. Parallel machines, we saw that a little bit in the case study about trying to schedule between parallel machines. Flow shop, serial system, like the tandem queuing system that we had. Flexible flow shop, things all follow the same general flow, but sometimes they skip machines and so on. And then we have the most flexible is something called a job shop, which we're going to talk about mostly here is kind of a variant of the job shop problem. Okay, and the job shop problem in theoretical scheduling has got to be one of the most studied scheduling problems in the world. If you were to search this on Google, there's no doubt in my mind you'd find many, many millions of hits on the job shop scheduling problem. So we're going to talk about, detail that here in just a second. When you talk about a scheduling problem, then you're thinking about, well, how do I create? So I gave you the 2 examples of the schedules in the previous slide. In order to choose between one or the other, or choose a schedule, you need to have some kind of objective. You know, what's the purpose of my schedule? And typical objectives that you see is something called minimize make span. We talk about make span, you have a set of jobs. So in the previous example, I had 7 jobs. And if my objective is to minimize the make span, then my goal is to create a schedule where the time that the last job finishes is the earliest. That would be a minimize make span schedule. But there are other objectives too. Minimize flow time. So flow time is the time that a particular job spends in the system, beginning to end. Maybe I have some kind of priority. I want to minimize the flow time for some class of jobs or something like that. Minimize lateness or tardiness. A lot of times jobs have due dates. So if you're filling customer orders, for example, and so lateness and tardiness are measures of due date, measures of performance in terms of due date. So you talk about lateness. Lateness can have negative values, like earliness. If something's due in 10 days and you send it in 7, lateness is going to be -3. A lot of times people don't care about earliness, and so that's what tardiness is. So tardiness is just the positive lateness. Okay? And then we have a whole slew of priority-based objectives that go into the general scheduling problem. I've given you a whole bunch of references here. As I said, if you look up scheduling, well, I said job shop scheduling, but scheduling in general, millions and millions. So these are not, this is not some super list of the best scheduling references. These are the references that I use. So that I have either taught from had classes from or just have used in classes. So they're here, and some of the material that I'm going to talk about comes from those books, or books and papers. Okay. We're going to talk about some terms, some concepts in scheduling. So we talked about jobs back on the first one. So sometimes we call them jobs, sometimes we call them parts, sometimes we call them orders, sometimes we call them entities, people, whatever. These are the things that you're trying to build the schedule for. Okay, and so when you think about a job, and so I'm going to either call them job or parts. That's typically what I refer to them as. A job has a set of operations. Okay, and operations, sometimes we refer to them as tasks. Tasks require resources, some processing time, and then you have some precedence constraints. So for example, if I said that I have a job that needs to be processed on machine 1 and machine 2 in our previous example, so we said that was R1 followed by R2. This job has 2 operations, J1 or R1 and R2. Each one of those has a corresponding time. And I have a precedence constraint that says I can't do R2 until I've done R1. Right? And so in the terminology here, that's what the precedence constraint for jobs mean. Jobs might also have a ready time. So in other words, they might not all be ready when you start your model. So in our arrival table example that I showed earlier, everything didn't arrive at time 0. Right? So from a scheduling perspective, that impacts how you solve the scheduling problem. I've already talked a little bit about due dates, priority, customer priority, or some other mechanism to make one job preferable over another job. Then we talked about bill of materials and raw materials that are required to do the task. So you could think about each one of these tasks might have some type of raw material associated with it, and then we have the bill of materials that might be associated with the job itself. I mentioned that back on the introduction, the bill of materials. We'll talk in more detail about that a little bit later on. Resources, we think of those as machines, servers, something like that. And we think about those as having either capacity, capacity 1, capacity 2, capacity 3, or some type of work schedule where it's available, like the one I showed up here, from 8 to noon. Then it's not available, then from 1 to 5. Okay, so I have work schedules. And the work schedules can have multiple capacity, right? So I could have 8 to noon, I have 2. Noon to 1, I have 1. 1 to 2, I have 1. 2 to 6, I have 2, or something like that. If you want to, if you have 2 people and they alternate their lunch, something like that. All right, so work schedule and capacity is really how we define basic idea of resource. Then we have some things that kind of cross boundary or combine both jobs and resources. And so particular setups, so I meant to add this here, sometimes called changeovers. You can add that here, setups and changeovers. And so we talk about a setup or a changeover, however you want to do it. I typically call them setups. Other people typically call them changeovers. Setups have to do with when I'm processing an operation for a job on a machine, do I have to do something to that machine before I start processing? Do I have to somehow set it up? Tooling, fixturing, or something like that. Okay? And there are 2 general classes that we're going to talk about, so-called sequence-independent setups and sequence-dependent setups. Okay? And the easiest way to think about that is if you think about like a painting operation. Right? So here's my painting operation, and here's my queue, and out in front of my queue, I have some green guys, some red guys. I don't have another color other than the standard black marker here, some black guys. Right? And if you think about this as a painting booth, when a job comes to be processed, there's a setup that I have to do. I have to load the paint. Right? So I have spray paint or whatever, and I have to like pour the paint in the machine. Okay? So that would be a sequence-independent setup, because when I do this one, I have to, add paint. When I do this one, I have to add paint. When I do this one, I have to add paint, and so on. There's also sequence-dependent setup that say, hey, look, if I'm doing a green job and then doing a red job, I have to wash the machine. Okay? So between this one and this one, I don't have to wash it because it's green and green. So I just pour more green paint in. But when I go from this one to this one, I have to do a cleanup operation, right? And I have to do that cleanup operation in addition to adding the paint. Okay, so that is a sequence-dependent setup, where the setup depends on the sequence of job. And of course, that's important because I might want to prioritize my job so that I don't have to do those setups. You know, if I compare this one to one that was like, okay, suppose I did green, red, black, green, red, I don't have enough hands, black, you know? Setup, the sequence dependent setups, setup. Right, so I can minimize my sequence dependent setups by prioritizing, you know, jobs that don't have to do that. And so that becomes a really important thing in terms of scheduling. Secondary resources, tooling, and operators for the setups, and this involves both setup and the processing. So I have a secondary resource, meaning maybe I need some particular tool. So instead of a paint booth, maybe this is a milling machine. And to do these green guys, I've got to have a particular fixture. Then when I do the red ones, I have to have a different fixture. When I do the black ones, I have to have a third fixture. Okay, and so in addition to the setup, you know, that imposes, so I have to change fixture 1 to fixture 2, I also have to have fixture 1 and fixture 2. Right, so that's a resource that's, you know, somewhere else, and I might share that between multiple machines. So that's what we mean when we say secondary resources. And then, of course, operators are typically referred to or typically considered secondary resources in the case maybe where, you know, when I have to switch from green paint to red paint, I've got to have a particular group of people come in and do the cleaning. Okay, so there's a secondary resource for that setup, okay, to do this setup operation. So that's what I mean when we talk about secondary resources. Okay, now a couple of concepts about schedules. Schedules and sequences are different things. Okay, people a lot of times use these interchangeably. A sequence is simply a sequence of operations in the scheduling domain. So let's say that I have I have my machine, the one I just had and erased. And let's say that I have J1, J3, J2, right? And they're going to come and be processed in that sequence. So this is my Simio model, for example. And if I look at what this looks like if this is R1, in my scheduling domain, what I'm going to see is something like this: J1, J2, J3. Okay, so J1, J2, J3 is a sequence. And this sequence imputes this schedule. But what makes this a schedule is when I attach start and end times. Okay, when I attach start and end times. So maybe this is 0, 5, 6, 8, or something like that. So I'm saying, okay, well, job 1 is going to start at time 0 and go to time 5. Job 2 is going to start at time 5 and go to time 6. Job 3 is going to start at 6 and go to 8. Okay, so when I do that, when I add start and end times, then it becomes a schedule. But that's not the only schedule that I can have for that sequence. So for example, I could do this. I could say J1, J2, J3, where, I don't know, this is 8. What would this be, 13? Let's say this is 15, 16, 20, 22. Same sequence. 1, 2, 3, 2 different schedules. Okay? Which brings us to our second definition, which says non-delay. A non-delay schedule is one where no machine that has an available operation is made to sit idle. So this one is a non-delay schedule. This one is not. Right? These guys right here and here and here, forced idle time. Forced idle time. Okay? So while we have a finite number of sequences, as we'll see in just a second here, if I have 3 jobs, I have 3 factorial, or I have 6 possible sequences, but I have an infinite number of schedules. Okay, I have 6 sequences, but I have an infinite number of schedules because I can have this forced idle time. And forced idle time can be anything. It doesn't have to be, 8. I could make it 8, 9, 10, 100, 3, 1, half a minute, whatever. Right? And so that's how I get this infinite number of schedules. Okay? Now, we might be thinking, why would I ever want to do that? Why would I ever want to have forced idle time? Okay, and we're going to see there are definitely situations where I want to have forced idle time. Like think about setups, for example. Maybe I want to delay something because I want to eliminate the need for a setup. Or maybe my ready times aren't 0. So maybe, this job doesn't arrive till time 8 because it's coming from somewhere else. I'm only thinking about this machine, but it's not available, so it's coming later. But I know it's coming. So I might say, hey, I want to incorporate this into my schedule, but I need to delay until it gets there. And so those are some simple situations where we would not only want to consider non-delay schedules. Okay, the two next ones, we're just going to really just hit the high point. We're not going to talk about these in detail, but an active schedule is a class of schedules. Okay, an active schedule is a schedule, see if I can get this definition right, in which the completion time for no job can be extended without making the performance metrics worse. And no, I'm not going to hold you to that definition. It's just a formal class of schedules. Okay, and it's going to hopefully be clear why I'm talking about this here in just a second. Okay, so just put that aside and say there's this class of schedules that are called active, and there is a formal definition of what makes it active. Regular measure of performance is, when we think about performance, a regular measure of performance is one that is non-decreasing in completion time. So what does that mean? It means that if I have a schedule, right, and I increase the completion time, like I did from here to here, I can't make my regular performance any better. I can't improve my regular measure of performance. Doesn't necessarily mean it gets worse, but I can't improve it. Okay? That make sense? And so, you might think that a regular measure of performance, we would always want that. Because, if I want to be non-decreasing, but if you think about like penalizing early time. Suppose I finish something, it's due at time 10, but I finish it at time 2. Well, it's 8 time units early. I might choose to penalize that because I might think, hey, this is bad, right? Because maybe it's some kind of pharmaceutical that has a spoilage time or something like that. Right? And so if you think about an earliness penalty, then it's not a regular measure of performance, because if I move the due date, if I move the completion time out, I've improved my performance in terms of earliness. Okay, so that's just one example of what that's not a regular measure of performance. Okay, so now the reason I brought these two things up is follows. If you have a regular measure of performance, the optimal schedule is guaranteed to be active, fully active. Okay? Non-delay schedules are subsets of active schedules, but not a complete subset. So that means that in general, the optimal schedule does not have to be non-delay. Okay, the optimal schedule does not have to be non-delay. Okay, and so back to my question of why would we ever want to consider something other than a non-delay schedule? Because if we want theoretical or optimality, we have to look more broadly than non-delay schedules. Okay? And that's the extent of what we're going to talk about active and regular measures of performance. So we're going to talk a lot about non-delay schedules because, as you're going to see, simulation-based scheduling and the whole bunch of different scheduling methods that are based on that, based on simulation-based scheduling, typically generate non-delay schedules by default. Okay? As we will see. Which brings us to dispatching rules, which we talked about a little bit. Talked about them in the video, and we've talked about it here. Dispatching rule is simply a way that I prioritize jobs that are waiting. So if I think about my resource here, J1, J3, J2, the dispatching rule says, when this becomes available, which one do I take? Okay? And so common dispatching rules, FIFO, first in, first out, or first come, first serve, last in, first out, shortest processing time, longest processing time, earliest due date, critical ratio, a whole bunch of different dispatching rules. Okay, with the idea being, when I take any machine, I'd like to be able to figure out which job do I take? How do I optimize my schedule by choosing the right one? Okay, and so that's where dispatching rules come into play. And in video 2 or 1, I don't remember which one of the ones in video module 1, we did that dispatching rule one where we switched it to SPT, showed how it changed the performance. Okay? So an important thing about when we use dispatching rules here is that what a typical dispatching rule does here is it just prioritizes things in the queue. So if I apply a dispatching rule here, it's almost always going to generate a non-delay schedule. Because unless you have a specialized dispatching rule, there is no rule that says, hey, don't take anything, right? So I have these 3 jobs, and I have a whole bunch of dispatching rules I can use, and what it's going to do is going to prioritize these 3, or it's going to give you a sequence for these 3, but there's not an option to say don't do any of them, right? Which is what I would need to be able to generate a non-delay schedule, at least in isolation. That's what I would need. Okay? Questions, definitions so far? So all of these things are really important. Active and regular measures performance, not a big deal. Certainly don't. I mean, I can't recite exactly what it means, so I certainly don't expect you to. But the whole point of that discussion was the idea that a non-delay schedule is not generally sufficient to guarantee optimality. You can have the best non-delay schedule in the world, doesn't guarantee optimality. Okay? So I'm going to do a simple example here. What time is it? 4:45. We should get part of the way through. I'm going to take a simple problem, simpler than the one we did on page 1. I only have 2 resources. I have 3 jobs. And what this sequence is telling me is that job 1 goes from R1 to R2. Job 2 goes from R2 to R1. Job 3 goes from R2 to R1. And those numbers in red are the processing times. Okay? Now, I just created at random. I think I did this at random. I'm pretty sure I did this at random. 2 different sequences, right, on both machines. So job 1, job 2, job 3 on machine 1, or R1, and job 1, job 2, job 3 on R2. And I constructed the Gantt chart. Okay, and it's pretty clear cut what's going on here. Right, I want to do start J1 because I want to have the sequence J1, J2, J3 on R2. I have that idle time there for the first 7 minutes because I want to have that same sequence. Okay, so that's why we see that gap there. If I choose to not do that, then I might say, hey, I can start job 2 on R2. It doesn't have to, it doesn't have to be the same sequence on both machines. Okay, so I might want it to be the same sequence, but it certainly doesn't have to be. And in a lot of cases, by altering the sequence, you can get better performance. Okay? So I just look at these 2 general cases. How many sequences on each machine? And how many schedules overall? And I have schedules here in quotes because, I mean non-delay schedules. Because we know there are an infinite number of schedules for any sequence, but what I mean is the imputed non-delay schedule. Okay? So I have 3 jobs on each machine. So there's 3 factorial, 6 sequences on each machine. And so in general, for n jobs, I have up there n jobs, I have n factorial possible sequences, right, on either machine. And how many schedules overall? Since I have 2 machines, 6 and 6, 3 factorial squared, 36. Or in general, n factorial to the m. Okay? Is n factorial to the m a big number or a small number? It's a big number. Get your little calculator out, and let's assume that we have 10 jobs, 5 machines. 10 factorial to the 5th is a big, big number. Okay, now remember, for each one of those, we have an infinite number of schedules. All we're talking about are the imputed non-delay schedules here. Okay, and so when people talk about the job shop problem, this is what they're talking about, is that the combinatorial optimization problem makes it very difficult. Okay, and actually impossible in the general sense to solve to optimality. Okay, so there's no point in really even working on it. Although there's a whole lot of research where people spend an awful lot of time doing this, trying to figure out ways to solve this problem better. Okay, that's really not our focus. Because also, if you think about this problem, this is the easiest scheduling problem you can have. Why? We haven't talked about setups. Right? We haven't talked about things like, okay, ready times. We're saying, okay, at least in this analysis, all the ready times are 0. Okay, we haven't talked about secondary resources where maybe I have to have an operator that's split between these tasks to do those setups. Right? So what we're talking about is a very abstract representation of a real, if you had a real job shop problem. This is a very abstract representation. But even with the abstract representation, we can't, or it's difficult to solve to optimality. Okay? But as I said, people try all the time, and there's tons and tons of research about this. And so a lot of the research, a lot of what you see is based on something called a disjunctive graph representation of the problem. Okay, so I just have this little simple drawing here. So what I did was I took our jobs and gave the operations individual numbers. So instead of just saying J1 and J1, I'm saying J11 and J12, right? And for J2, it's J21 and J22. Okay, and so each operation is uniquely identified. And so this is what's called a disjunctive graph representation. And so in this representation, the blue arcs are the precedence constraints, which says for part 1, it goes, from J11 has to be done before J12. That's the precedence constraint. For job 2, J21 has to be done before J22. That's that middle blue up precedence arc. And for 3, 3.1 has to be done before 3.2. So those are the precedence constraints. Okay? The colored arcs, the red and green ones, are what are called disjunctive arcs. Okay? Disjunctive arcs, hence the name disjunctive graph representation. The disjunctive arcs represent particular resources. Okay, so in mine, the red ones represent R1. Because I know J11 is performed on R1, J22 is performed on R1, J32 is performed on R1, and the green arcs are for R2. Okay, and notice on these arcs I have a pair, I have a disjunctive pair between every node. Okay, because the precedence there is no natural precedence here. There's no natural precedence here. Right? The natural precedence for the operations is the blue arcs. Okay? So I can take that disjunctive representation and create what's called a selection. So a selection says, I'm going to take one of these little cliques. So if you look at the machine, the red ones or the green ones represent R1 and R2. So in graph terminology, those little arcs associated with the machine 1 form a clique. Machine 2 form a clique, right? So if I take the disjunctive arcs from a clique and select one from each pair, that's what's called a selection. If I make that selection acyclic meaning there's no cycle, obviously, now I have a sequence. Okay, so if I take that acyclic selection for my R1, for my R, let's see, red was R1, that imputes the sequence J32, J11, J12. Similarly, if I do the same thing with my green one, which is R2, I pick another acyclic selection from that disjunctive set. Okay, now I have a sequence on it. Okay, so now I have a sequence on R1, sorry. I have a sequence on R2, and from that I can form my schedule. Again, schedule in quotes, because I'm not thinking about inserting idle time or anything. I'm just taking the simplest non-delay imputed schedule from that sequence. Okay? So if you look in the job shop scheduling literature, you're going to see a lot of stuff like this. Because they're going to talk about the job shop scheduling problem is really this problem of finding what are called complete selections. So if I have a selection from every one of my cliques, and it's completely acyclic, then I have a schedule. So you want to do things like find the complete acyclic selection that minimizes the make span. Right, so again, when you talk about the theoretical or the formal definition of the problem, and then once I do that, I can formulate the problem mathematically, and away I go. Yeah?
You just go to the previous slide.
The what now?
I have a question about the previous slide.
Okay.
So, is there any particular reason we're choosing to go from J32 to J22 instead of J11?
I just did it arbitrarily. Okay. Yeah, so again, there are 6 of them. So if you look at that, if you look at the 3 operations that are on one, there are 6 sequences, which means there are 6 acyclic selections, and I just arbitrarily took one.
That's an example. The schedule.
That's just an example.
Okay.
Right, so if you want to optimize it, it's trying to find the optimal one of those 36 that are, the combination of both. Okay? Does it make sense? Okay, so again, this is the end of our theory stuff. We're not going to have, I don't remember. Do we do any more equations the rest of the semester? I can't really remember. We might do one or two, but we're not going to do anything. And we're not doing anything with this formulation. I only put it up there to show, as I said, there's just reams and reams of research on this problem. And so if this is something that's of interest to you, it's a really nice representation of the problem. And understanding that representation will let you get or have access to a whole bunch of work in the area. And I have a paper here that's, that talks about different mixed integer scheduling problems, and that's where this specific formulation came from. If you want to look at this paper, let me know. I have that paper, and I would be happy to share it. Okay, so the last thing I want to do today is I want to talk about something called schedule generation. Okay, I'm just going to do this really quick example because schedule generation is a basic methodology that works almost the same as simulation-based scheduling. Schedule generation is kind of the basis for simulation-based scheduling. So I'm going to do this pretty quickly because I only have a few more minutes left, but I should have plenty of time. General scheduling generation algorithm, what I'm going to do is I'm going to define little t as something called a task cutoff time. I'm going to define 3 different sets. One set is U of unscheduled tasks. One set is P is the set of precedence feasible tasks from U. And then S is going to be the set of what are called schedulable tasks from P. So this whole schedule generation says form U, form P, form S, pick one, schedule it. Adjust U, adjust P, adjust S, pick one, schedule it, and you just cyclically go through. Okay? And so here's how this works. Initialize U while U's not empty. Update P, so I just move everything that I can from U to P. Then for each task K and P, I'm going to compute the earliest start time for that task. Then I'm going to define my cutoff time T as the minimum start time from P. Then I'm going to let S be all of the tasks. My schedulable tasks are all the ones from P that have the earliest start less than or equal to T. Select a task, add it to the schedule, remove it from U, do it again. Okay? Let's take a quick look at our little example here, and hopefully that'll make sense. So this is for my reference here. Here's our problem here, R1, R5, J1. And so this is the one that we did J11, J12, J21, J22, and so on. Okay, so let's look at our schedule generation here. So here we are. I got R1, R2, and the process basically says, okay, let's define U. U, of course, when we start, is going to be everything because nothing's scheduled. So I'm going to have J11, J12, J21, J22, J31, J32, everything. Okay? Then it says, okay, take those things from U that are precedence feasible and put them in P. Of course, all our jobs go from, either R1 to R2 or R2 to R1. So these guys are precedence feasible, these are not. Right? So I'm going to have J11, J21, J31. Okay, because I can't do 1, 2, because 1's not done. I can't do 2, 2, can't do 3, 2. They're not precedence feasible. Next step says calculate the earliest start time for each job. Well, I look at my machine, my resources, start at 0, so my 0, 0, 0 for my start time. So my cutoff time T is equal to 0, and now I can form S. S is J11, J21, J31. Okay? So we're going to pick one. Okay? Let's pick J11. Okay? And then I schedule it. So J11 takes 5 time units on R1. So time 5, J11. Okay? Go back to the top. This guy's gone. Go back here. This one's gone. J12 is now precedence feasible because J11 is scheduled. So it's now precedence feasible. So now my precedence feasible are J12, J21, J31. J12 can start at time 5, right? Because it has a precedence constraint with J11. So its earliest start time is 5. This one is 0. This one is 0. My T is still 0. Just erase that guy, and those are my schedulable tasks. So we pick one. Let's pick this one, J31. J31 is on R2 and takes 1 time unit. So here is 1, J31. J31 is gone. Gone from there, but now J32 is feasible. I look at my start times. J12 can still start at 5. J21 can start at 1. J32 is up here. It can start at 5. Okay? So now T is the minimum of those. So T is now going to be 1. And so this is the only one there. I'm going to schedule that one. 2-1 takes 3 time units. So it's going to be here at 2-1 times 4. Okay? So now 3-1 is, let's see, 2-1 is gone. 1-2, 3-2, 2-2, J2-2, J12, start at 5, 5, 5. All right? Pick one. Let's do this one. So, oops, this was 5. I guess I kind of skipped the step of putting them in schedulable. Sorry about that. But I just picked this one out of here. So then I'm going to do 1, 2. So this is at 5. And it takes 2 time units. So it's 7. J1, 2. Now, it's done. Now my precedents feasible are J22 and J32. Both of those are here. So they can both start at 5. So I'm going to pick one, then I'm going to pick the other one, and I'm done. Okay? So pretty straightforward process. Just a matter of managing these 3 lists. Okay? Now, we're going to talk about this a lot, so we're going to come back Tuesday because I'm not going to have time to finish everything I want to talk about, but I want to leave you with 2 things to think about between now and our next class. A couple of steps here, we really didn't talk about why we do. For example, why did we set T equal to the minimum start time? I suppose I didn't do that. Right? If I don't set T to the minimum starting time, then I'm expanding those things that I can schedule. Okay? If I have this rule, setting T equal to the minimum, then I'm guaranteed to create a non-delay schedule. Otherwise, I'm not. Okay? And in fact, I can't show, it can be shown, that if you want to generate active schedules, then you have to set T equal to the completion time, not the start time. We're not going to do that, but it's just something to keep in mind. Second thing that we didn't talk about at all is how to select task K from S. We have these schedulable things. Regardless of how I set my cutoff time, I have a whole set down here. I just arbitrarily chose them. Well, how do we choose them? How do we choose those well? Okay, how do we choose those well? Okay? Think about that. Make sure that you can generate this. Again, it's a pretty straightforward process, but this does form the foundation of simulation-based scheduling. So next, what day? Tuesday. Next Tuesday, I will pick up here, talk a little bit more about schedule generation, kind of transition into simulation-based scheduling, and then do carry on from there based on what we saw in the video module for this week. Okay? All right, thanks. If anyone has any questions, again, to Canvas. If you have any questions about the case study or the video modules or Simio or any of that. Thank you very much.
Are you okay? Yes, no.